before we move on, though? Okay. If not, we'll go ahead and move forward. Okay, so the Cascode circuit is another form of multi-stage amplifier circuit. It still only uses one transistor type, so we still are avoiding using P-type transistors in this case. There's lots of amplifiers you can make that use complementary MOSFET transistors, P-type and N-type, and they're very, very helpful. We'll talk a little bit about them in the next test, just because it's important to look at CMOS, which means we'll have to understand how P-types work again really quickly. But this circuit, again, is only an N-type transistor. I am going to draw it the way the book draws the circuit, just so you're familiar that they're drawn multiple ways. And so this is another way of drawing the N-channel MOSFET. It's just another way of writing out the same kind of circuit. So don't think too much into it. Something I am going to note here is that there is no capacitor on the V out, which means it's also going to be coupling your DC V out as well. There's times when that's helpful to do. So it's not like you always have to have a capacitor with your output voltage. But it just means that the circuit after it would impact the rest of your circuit for DC analysis as well. So it has some design concerns you have to worry about, but otherwise, it's a very reasonable thing to do to pass the DC output. And so this is a kind of a weird looking circuit. I'm going to, again, do the detail from the book just because they do a really good job of making the math work out nicely. But the big advantage of this circuit, as we'll see later on in this class, is higher frequency response. So if you have an application where you have to move to higher frequencies than you would typically use for a MOSFET, this type of circuit is helpful in that you would get a much higher frequency response than a traditional Cascade MOSFET amplifier. But it is a little bit weird to think about because we're going to basically going through two transistors in series. And that's not, again, a concern in any case, but it's just something that we have to take into consideration as we solve this. We're going to assume these are two identical transistors where K equals 0.8 milliamps per volt squared, and VTN equals 1.2 volts, and lambda equals 0 inverse volts, which basically means we get to ignore early voltage. It's a big deal because this circuit would suck with early voltage. So again, we're ignoring the DC analysis of this. We're saying that IDQ equals 0.4 milliamps. If you want to go through and solve it, you'll get that answer, approximately. They're rounding a little bit there. That's okay. So step 2, we've done our DC analysis. We have to go through and say, what is our small signal parameter? Again, we're only going to have really one in this case, and that's because IDQ is the same for both of them. Both of these transistors play a role in the DC analysis, which is why we're skipping the DC analysis and just solving it directly, because we haven't done that level of problem for DC. But in this case, GM1 equals GM2, which equals, again, that 2 times the square root of 0.8. That's milliamps per volt squared times 0.4 milliamps. These are in series. They have the same current. And that's going to equal 1.13 milliamps per volt is the transconductance. Now we have to build the small signal equivalent of this circuit. And it's not as bad because a lot of these things are going to become kind of easier. So first of all, we have a short to ground for this gate. We have a short to VIN for this gate. This is a path to ground. And this is a bypass path to the ground. Because again, this is a bypass capacitor. It allows us to stabilize our DC values of our transistor, but still get a fairly large amplifier gain. And so, because of this, VIN never goes through R1 up here. Because if we could look at this, it's going to take a short to here as opposed to going around through R1. So we get to ignore R1, our small signal components. RD will matter to us, so this path to ground still matters to us, but essentially this path is going to be ignored. This path is going to be ignored because this path goes to ground. And so we can rewrite this as, and again, I can erase these a little bit real fast and replace them with their small signal equivalents. So this is a path to gate. This is a path to gate. This is RD, and then we have a path like so, and like so. So this is GM1, VGS1, GM2, VGS2. So if we go to redraw this circuit, we can start with VIN. And VIN it's going to have two parallel paths to ground because we don't have a source resistor through R3 in parallel with R2. And we can write this again as VGS1. Oh, I did that backwards. Okay, that makes a lot more sense. Okay, I apologize. This is backwards. Thank goodness. I was lost for a second there. I apologize. This transistor is transistor 1, so this is GM1 VGS1. This is GM2 VGS2. So this is transistor 1, which makes a lot more sense because this is gate 1 right here. And so, right here, we have GM1 VGS1. And over here, we also have this right here. And this is GM2 VGS2. Because of the way the circuit is designed, these are completely equivalent. Excuse me. Because again, G2 is right here. It's essentially going to ground, but it's not because of how it's actually designed. And so it's just going to look like this instead. RD. And V out. So essentially, transistor 1 supplies the source current of transistor 2. with GM1 VGS1, resistor 2 basically acts as a current follower. Whatever this one does, this one's going to be the same, because its ground value is 0 here. And so it's going to just take the same current value as this one. So basically it's going to be it's called a current follower. It's not going to change its value at all. And that's because VS is right here for this one. Whereas right here, this is VS. So it's going to have the same value for VD as this one has for VG. So essentially, it's going to just be a current follower. So this current is what's really going to drive the entire circuit. Which means we can write V out as just negative GM1 VGS1 times RD. Because again, this is a current follower, so it has the same value. Since VGS1 is just equal to VI, because again, we have no RS right here, it's ignoring that. Our small signal voltage gain AV is just equal to negative GM1 times RD. And then finally from there, we can just say that the circuit AV equals negative 1.13 milliamps per volt times 2.5 kiloohms, which is going to equal negative 2.83 volts per volt. So if you think about this, if you didn't have that top transistor, would any of this circuit analysis have changed other than being annoying to figure out? And the answer is no. And that's important to realize. This top transistor does not change the common source amplifier that we had before. So V out still right here. This extra transistor is not changing anything about how this circuit is solved. Again, this just has the same current value. It's not applying extra current because these are not two parallel paths converging. These are just two paths in series with the same current source. So instead, it's basically not changing anything about the circuit. But as I said before, the purpose of the circuit is a higher frequency response. So when we actually dive into these circuits again later on in the course, we'll see that the addition of this second transistor right here really pushes the frequency response of the amplifier up quite a bit, and essentially allows us to have a higher frequency response range than just a simple single transistor, which is really helpful in a lot of applications, because if we want to have something that goes to gigahertz range where a lot of our communication works, a single transistor is not going to cut it, and so we have to redesign the circuit to work where we can push it to higher frequencies without completely changing the material properties of our entire transistor. So that's why we use these types of circuits. Again, we're going to come back to this later on. I wanted to show it to you now so that, hey, we went through it. It's a good practice. Drawing this equivalent circuit is not something that you do on an exam, so don't panic. It's a little bit weird. The reason this gets away with this is because essentially VD for this one is at V out, right? And VS for this is right here. Where this is also VD1. But VG for this one, which we can't see, is ground, which allows us to work out the exact same way. Because this is VS1, so VG2, VS1. And so they're just negating each other. So it's just, again, would work out the same mathematically. A little bit weird of a jump to get to that. There's a couple steps you'd really want to take to do this. But essentially, this works out the exact same way. The biggest thing to take away is this is a source follower, current follower. Do not panic about this being here. hey, it doesn't do anything. Just give us the same answer. With that, I do need to quickly take roll for people who are in class, and then after that, we are done for the day. We're a little bit earlier than I thought we'd be, because I thought Cascode would take me a little bit longer. Friday, we're going to do a couple of practice problems, just to kind of review everything we've covered the past long time. But this is the end of new material. Friday, we're practicing. Monday is going to be a review day, and then next Wednesday is your exam. So I'm giving us a lot of time to go back over things, because if we don't do so, it'll, you will, If we don't do so, there's a lot of material. I want to make sure we answer questions, practice everything we've covered again a little bit. So.